Hello everyone, this is part 7 video on past year NEET questions from the topic electrostatics and capacitors. Now those who are looking at this video can take a look at the previous parts so that you'll have continuity of questions. We'll start with a question that has come in the year 2001. It's a rather straightforward question, formula based question. A dipole of dipole moment P is placed in a uniform electric field E, then the torque acting on it is given by. So if you consider the dipole to be placed in a uniform electric field, let us say the electric field is here towards the right side. It's a uniform electric field. That is why we are representing with parallel lines which are equally spaced. So this is placed in a uniform electric field. Maybe it can be placed with some orientation with respect to the electric field. Let's say theta is what the angle between P and E vectors, because the dipole moment is also vector. They are asking what is the torque. So torque acting on the dipole will be given by the cross product between the dipole moment with the electric field. So in terms of value, it is going to be, the magnitude will be PE sin theta. But here anyway, the basic formula, torque vector formula, is what we have to look at. Correct answer is option B. It's a straight formula question. Next we have a question based on capacitor. Energy per unit volume for a capacitor having an area A and separation D kept at a potential difference V is given by. Means we have a capacitor, parallel plate capacitor. Area of cross section is A, distance between the two plates is D, and the potential difference is V. For a parallel plate capacitor, the electric field in the region between the two plates will be given by potential difference divided by D. The electric field which will be uniform throughout the region will be what? If this is the positive plate and this is negative plate, it will be from positive plate to negative plate. The value will be potential difference divided by D. So here they are asking energy per unit volume. Energy per unit volume, that is what is energy density. Energy density is what? Half epsilon naught into E square. In any region where there is electric field, energy density will be half epsilon naught into E square. So in place of V, we will simply substitute V by D. Half epsilon naught into V by D the square, which is what? Half epsilon naught V square by D square. Correct answer is option A. It's again very basic question on the energy density formula, because in fact the derivation for the energy density, right, we'll actually do by using a capacitor, but this formula, the energy density for an electric field, is something that we'll use everywhere, including the discussion about the electromagnetic waves. Next we have a question based on the electric flux. A charge Q microcoulomb. Microcoulomb means what? If you have to express this value in terms of SI unit, means it will be what? Q into 10 power minus 6 coulombs. In terms of coulombs, the value will be what? Q in 10 power minus 6. A charge Q microcoulomb is placed at the center of a cube. The flux coming out from each face will be, if you think about a cube, let us just represent a cube. So we are placing this particular charge at the center of the cube. So let us say we are placing a charge at the center of the cube. Now for every cube we'll have 6 faces, like 1 2 3 4 lateral faces, and 1 below and 1 above. So 2 faces which is above and below. Totally we have 6 faces. All are symmetric. So when we observe from the center, all will be symmetric. Means from the charge we are keeping at the center, let us say some 100 field lines they go through the phase 2. Because of symmetry, same 100 field lines will have to go through phase 4. Same 100 lines have to go through phase 5, like that. Which means the flux will be distributed uniformly. So if the flux through total cube, which is the enclosed surface here, has to be linked to the flux through each phase. Let's say, each phase the flux is what? 5 phase. The total enclosed surface flux will be 6 times the flux through each phase, because we have 6 phases. Now as per the Gauss law, right, flux through the enclosed surface is what? Charge inside by epsilon naught. So in terms of the SI unit, what is the charge? Q into 10 power minus 6 divided by epsilon naught. This is what is the flux through the enclosed surface. But here they are asking what is the flux coming out of each phase. Means this is what? 6 times the flux through each phase, right? So we have to bring the 6 this side. So what is it? Q into 10 power minus 6 by 6 epsilon naught. That is what is flux through each phase, which is our option A. In fact, no, this flux through each phase kind of question, right? I think it has come in one of the other previous years also. So particularly measuring the flux by keeping the charge with respect to a cube, right? Already we have seen, when charge is placed at the corner of the cube, what will happen to the flux through the cube, like that. We have seen different kind of models on the flux linked to the cube. So while we are discussing about it, I think the next question itself is again on the flux linked to the cube. A charge Q is situated at the corner of a cube. So where is the charge situated? It is situated at the corner of the cube. The electric flux pass through all the 6 phases of the cube. Means they are essentially asking what? You have a cube where the charge is placed at the corner. Charge is not placed at the center of the cube, it is placed at the corner. And they are asking, so here where we are keeping the charge, they are asking what is the flux through all 6 phases of the cube. Means essentially what they are asking, the flux through the cube. So whatever the given cube that we are representing, they are asking what is the flux through the cube. Now this is a concept that you would be covering in chemistry solid state chapter also. So if you have an atom which is kept at the corner of the unit cell, so this cube, you can think of it like what? Unit cell. This atom or particle, whatever, in this case it is charged particle. The contribution to the unit cell will be 1/8. If you keep an atom or particle at the corner, means contribution for the unit cell will be 1/8. Means you keep a charge Q at the corner, the part of the charge that will be inside the cube will be only 1/8 of it, which means it is what? 1/8 times Q. The remaining 7/8 times Q will be outside. Now as per the Gauss law, right, flux through this enclosed surface is what? Charge inside. What is charge inside? 1/8 times Q divided by epsilon naught. That's it. What is the answer? Q by 8 epsilon naught. So option B will be the answer. The same thing we can also try to explain in different way. See, here if we have just that one cube, we are not able to enclose the charge. The way in which we can enclose the charge is if we consider 7 more such kind of cubes identical. The one that we are already having is 1. Let us say 2, 3, 4. 4 in that one plane. Similarly 5, 6, 7, 8 exactly above. So that corner position, right, is shared by basically 8 cubes. So the way we have one cube, we consider 7 more such identical ones arranged like this. Now for this bigger cube we are considering, right, this charge is perfectly inside. So flux through the bigger surface is what? The charge Q is perfectly inside now, which is Q by epsilon naught. But as you can see, the field lines from this charge will go uniformly in all directions. Means what? You have 8 cubes. So each of them will contribute equally. So total flux will be what? 8 times the flux through each cube. That is what? Q by epsilon naught, which means flux through each cube will be equal to what again? Q by 8 epsilon naught. We are going to get the same answer. Either we take the previous approach or this approach, we will get the same answer. What is it? Q by 8 epsilon naught. A thin conducting ring of radius r is given a charge plus q. Means you can see here, this is the conducting ring. So this is given a charge. Where the charge will reside, it will be residing on the entire perimeter or the circumference. The electric field at the center O of the ring due to the charge on the part AKB. Where is AKB part? This is the AKB part. Due to the charge on the AKB part, the electric field at the center O is E. The magnitude of this is given as what? E. The electric field at the center due to the charge on the part ACDB. So where is this ACDB portion? ACDB is nothing but the remaining part, leaving out that AKB, right? The remaining part of this ring is what? ACDB. So we need to find what is the field because of this ACDB part. So here we'll have to understand one thing. The ring is symmetrical. Now what happens because of this symmetry is, if we consider a small charge portion over here, let us consider a small charge portion. This will develop electric field since it is a positive charge ring, right? Away. Consider a symmetrically opposite charge. This will develop electric field exactly in the opposite direction. So wherever you take, let's say this is element 1, this is element 1 dash. We can take an element 2 here. There will be a symmetrically opposite 2 dash. Because of which the electric field will get cancelled. So the net field at O will be 0. So at the center of the ring, the net electric field will be 0. Which means if due to the part AKB, if AKB is developing an electric field E, then the ACDB part, remaining part, should develop electric field which will be equal in terms of magnitude but exactly opposite in direction. That is when they both will cancel, so that the net field at the center will be 0. Which means straight away what we can say, option C cannot be the answer. Option B also cannot be the answer. Because the electric field due to the ACDB part should have equal magnitude as that of the electric field due to the AKB part, which means this should also be having the same value E. Now comes the question of the direction. So let us look at first the AKB part. So we look at the AKB part. Now draw the line connecting O and K. We'll see what is significance of this, because in both these options you are seeing this O and K. Draw the line. This is what will be the symmetry line. Now take a small charge element on this side and symmetrically charge element on this side. So field because of this element will be in this direction. Field because of this element will be in this direction. What happens is when you resolve them into components, right? It will have one component like this, another component. Let's call them as what? DE1, DE2. DE2 also, when you take components, it will have a component along this direction and another component. So what we see is these two components, right? They will cancel because they're symmetrical. They will cancel in terms of value, which means the field will be along which direction? This line is what we'll say K2O. So the overall field due to the AKB will be in the direction of K2O. which means due to this ACDB portion, right, the field must be, already we got the value of the field E, but direction must be exactly opposite. Means what? It should be E in terms of value along opposite direction. Means what? O2K. Field because of AKB is in this line K to O. Field because of this ACDB will be O2K. So this direction it is going to be. So this is the direction. So what is the correct answer for this? It is option D. So this question is more about how do we reason. Next we have another these kind of models nowadays we are not seeing because it involves a little bit of integration approach, but it's a good question. Maybe this can be taken as a standard result. So since in one particular year they have given a question with parameters, like they have used lambda a like that, right? Maybe in future if they are trying to give a question on similar example, they might give a question with values. That's something that we need to be prepared for. Electric field at center O of the semicircle radius A having a linear charge density lambda is given as. So we have a semicircle, the semicircular portion, right, is having a linear charge density lambda. We have to find the field at the point O. We have to find the field at the point O. Now if you look at the semicircle, let us look at this center line. This is what? The line of symmetry. We'll see what is the use of this line of symmetry also. So here what we will do is from this end, after covering an angle theta, we will consider a small element which is spread for d theta angle. The element is having an angular spread of d theta. So the length of this will be what? Radius is a, so the length of this element will be a into d theta. Charge on this will be small amount of charge. Charge will be equal to what? Linear charge density into length. Now this element will produce electric field like this. This is the small electric field. Now if we consider a symmetrically opposite element on this side, what it will do is it will also produce electric field, but in this direction. So if you take the components, this can be resolved into two components. One component will go like this. Let's say we call it as DE1. Other component will be DE2. This also we can resolve into component. One component will be this DE3. Other component will be DE4. Essentially what we see is that the DE3 and DE1 will cancel. So we are just going to be having the component that will be along this line of symmetry. That is what is going to be the remaining part. Due to the symmetrical shape of this semicircular ring, the component of the electric field which is along the line of symmetry will be remaining. What is this? If you look at it, right, this is theta, means this angle will be theta. So component this side will be DE sine theta. That is the component that will be remaining. So DE value is what? For this element, this point is at a distance a. So DE will be 1 by 4 pi epsilon naught dq by a square. So 1 by 4 pi epsilon naught dq is what? Lambda a d theta by a square. So 1a is cancelled. Now this is DE. We require DE sine theta, which means what? 1 by 4 pi epsilon naught into a Numerator we have lambda d theta into sine theta. This is our component of the electric field along the line of symmetry. Now this has to be, so we'll cover the entire portion of the ring when we'll do this integration, when we'll complete the integration, as the theta value is changing from 0 to pi. So when we integrate this electric field component from 0 to pi, that is when we will be able to get what is the total or net electric field due to that semicircular ring. So now our job is just to complete this integration. So net field along the, so net field will be along the line of symmetry. Total net field will be only along the line of symmetry, will be equal to what? Integration, which is 0 to pi 1 by 4 pi epsilon naught a lambda d theta sine theta. In this entire thing is a constant, it will come out. So lambda by 4 pi epsilon naught a integral 0 to pi sine theta d theta. So here we have to use some of the standard integration relations. Integral sine theta d theta will be minus cos theta. Integral sine theta d theta will be minus cos theta, which means here when we are concluding the integration, lambda by 4 pi epsilon naught a integration is going to give us minus cos theta. Limits are what? 0 to pi, which means lambda by 4 pi epsilon naught a will have minus cos pi, then minus of minus cos 0, minus cos pi is actually minus 1, so minus of minus will become plus. Here also minus of minus will be plus, so totally 1 plus 1 will be 2. The final answer is 2 lambda by 4 pi epsilon naught into a. So we can cancel 1 2, we can cancel 1 2, 2 1s are 2 2s are, so it will be what? Lambda by 2 pi epsilon naught into a. Lambda by 2 pi epsilon naught into a. So what is the correct answer for this? It is option C. So all that we are doing is we are looking at the small element of the ring, and based on the symmetry we are able to identify that the net field will be only along the line of symmetry, and that we are able to get total value of the field because of this ring by using the integration approach. So this is, as I said, right, these kind of questions we are not seeing much nowadays because of the extent of these mathematical application that is involved, but definitely this result can be something that is going to be useful for us in future examination. Like I mentioned, right, sometimes what they do is in 1 year they have given us a question based on the parameters. Maybe in other future papers, right, we might see similar type of question given by using the actual numbers. So that's how we need to be looking at. Next we have a question that has come in the year 2000. A capacitor is charged with a battery and energy stored in the capacitor is U. After disconnecting the battery, another capacitor of same capacity is connected. So after discharging it, we are connecting another capacitor of same capacity in parallel to the first capacitor. Then the energy stored in each of the capacitors is how much? That is the question. So look at it, we have a capacitor whose capacitance is, here they have not given the values, but let us say C. We are connecting across a battery of voltage V. Then the charge on this capacitor will be equal to what? C times V, and energy will be half CV square. Let us keep it. Now after disconnecting it, we go and connect it across an identical capacitor. Means this is C, but it is charged, this is uncharged initially. what would happen is there is going to be charge transfer. So this is having a charge Q. We know what is the Q value. What is the Q value? C into V, right? So finally, because they are identical, right, the final charge on each of the capacitors will be, there will be equal distribution of the charge. Both of them will have a charge of Q by 2 and Q by 2. Both of them will have a charge of Q by 2 and Q by 2. Now capacitance is C. So here we can see that the energy on any capacitor, they're asking what is the energy stored in each capacitor. Energy will be what? Let us say this is U1 will be what? We can use charge square by 2C. What is the formula we can use? It is what? Charge square by 2C. Now charge square means what? This is Q square by 2 square will be what? 4. 4 will come to the denominator. Already there is a 2, right? Which means what? 8C. But Q is what? CV, right? Means C square V square by 8C. 1C will be cancelled. What is it that you have? That U1 is equal to what? 1 by 8 CV square. So if you compare the equation 1 equation 2, what do we get? U1 value is nothing but 1/4 of U. So the final energy on each capacitor will be what? 1/4 of the original energy. So if you even add, so we got our answer. What is it? Option B. Even if we add identical, right, this also will have U2 also will be what? U by 4. If you add both of them, U1 plus U2, we'll get how much? U by 4 plus U by 4, that is going to be U by 2. So half the energy will be lost. In this charge transfer, half the energy will be lost. And of course that lost energy will be going in the form of the heating of the wire components, etc. That is an energy that is dissipated. In fact, we got questions in previous years based on that also, like what percentage of energy is lost, etc., etc. Okay, so here what is the answer for this? It is option B. Next we have a really good model question. This has come in the year 1999. This is called as the analogous to balanced Wheatstone bridge, because we'll talk about the Wheatstone bridge concept in the electrical circuits. What is it? If you have the combination of resistors, 5 of them connected, 4 across the sides of the quadrilateral, 50 is along the diagonal. Across the second diagonal, right, we will keep the voltage source or the battery. That is how we will have the circuit. Let's say this is R1, this is R2, R3, R4, and this is R5. If R1 by R2 is equal to R3 by R4, if that balancing is met, this ratio is satisfied, then no current will flow through R5, which means this R5, though it is physically present, it is like redundant because no current is going through that. So we will see that the circuit, though it looks complicated initially, this can be simplified because of the balancing condition. So the combination of capacitors here given, if we take a closer look at them, initially we might not be able to see which is series, which is parallel, because obviously there is no two capacitors in series, no two capacitors in parallel. So we cannot say that, okay, this C1 and C3, they are not in parallel. C3 and C5, they are not in series because there is some junction coming in between. But if you take a closer look at them, right, the same arrangement of the capacitors can be represented like this. So this is our A, this is our point D, this is B, this is C. Look at this, across B and C, between B and C, what do we have? 20 microfarad. A and B, between A to B, what is there? 6. A and C also 6. C and D, there is 6. B and D, there is 6. So this is a very standard modification, that is what we call it as. Though we are mostly familiar with this kind of representation, right? So whenever we say Wheatstone bridge, we are used to this kind of representation, but it's after all a circuit, right? We can represent the way, I mean, we draw the diagram. So this is also nothing but what, if you just try and modify it, it will also look like a Wheatstone bridge. In fact, the arrangement will be same. These two arrangements are what, identical. It's not like we are modifying the arrangement of capacitors, we are just redrawing it. We are redrawing it so that we can clearly see that this is like a Wheatstone bridge. Now you see the 6 by 6 is equal to here 6 by 6 means what, this is balancing condition. So the diagonal capacitor will not get a charge. In the case of the electrical circuit Wheatstone bridge, the diagonal resistance will not get current. Here this will not get charge, means though it is physically present, we can take it out because it is redundant. Now you see what is there. There is an upper branch. There is an upper branch in which we have two 6 microfarad capacitors in series. Now this is gone. And there is a lower branch in which we have again two 6 microfarad. So 6 and 6 in series means what? C equivalent is C1 C2 by C1 plus C2, right? Means what? 6 into 6 by 6 plus 6, that is what? 36 by 12, which is 3. So the equivalent of this is what? 3. Similarly identical, right? Below also it will be what? 3. Now what do we see? The 3 microfarad and another 3 microfarad are in parallel. So overall equivalent will be what? Parallel means C equivalent is equal to C1 plus C2. That is what? Totally 6 microfarad. So correct answer is option D. So here the trick in this problem is to identify that this is like a Wheatstone bridge with regard to capacitors, and also to see that this is a balanced Wheatstone bridge. Once you are able to find that it is balanced, they will knock off that diagonal capacitor. Then it's a very straightforward question that we are very familiar with. Okay. Next we have a question based on the dielectric constant. When air is replaced by a dielectric medium of constant K, the maximum force of attraction between two charges separated by a distance. Means what? If you have two charges, let us say charge Q1 and charge Q2, they are separated by a distance D. Now here we have the medium is what? Air is the medium. Force between them is what? 1 by 4 pi epsilon naught modulus of Q1 into modulus of Q2 by D square. If instead of keeping the charges in air, we will take the charges to another medium whose dielectric constant is K, means for this medium the permittivity value will be what? K times epsilon naught. Force in this case will be what? F dash 1 by 4 pi epsilon modulus of Q1 into modulus of Q2 by D square. But what is this epsilon? K times epsilon naught. So what we see here is that this F dash is nothing but F by K. So when we change the charges from the air to another medium, the force of attraction, or if the charges are same type, means they will repel. Okay. So the force of attraction between them will be what? It will be decreasing by K times. What is the correct answer for this? It is option C. Next we have a question that has come in the 1999. In bringing an electron towards another electron, means we have an electron, we want to bring this electron towards another electron. The electrostatic potential energy of the system. What happens to the electrostatic potential energy of the system? So look at it. Initially, let us say the distance is what? D. Potential energy will be K. Electron each charge is what? Minus E, right? Divide by D. So what is it? K E square by D. When we bring them towards each other, means they are coming closer. We'll just answer this question by taking a specific value itself. Let's say we bring them closer and the distance between them now becomes d by 2. It may become d by 3, d by 4 also. Let us just take some d by 2. Now in this case, what is the potential energy? Let's say this is initial, this is final. What is the potential energy? K into minus E into minus E divided by d by 2. Distance now is d by 2. So what is it? 2 will go to the numerator. 2 times K is square by d. So what is happening? The potential energy of the system is actually what? Increasing. Potential energy of the system is what? Increasing. So what is the correct answer for this? It is option B. So when you bring these, not just electrons but like charges, when we bring the like charges together, the potential energy of the system will be increasing. When you bring unlike charges together, means one side positive, one side negative, then the potential energy of the system will be decreasing when you bring them together, means that is for the unlike charges. A parallel plate condenser. So I think we might have discussed about this. Condenser is basically representation of what? Capacitor. A parallel plate condenser with oil between the plates. They are giving us the dielectric constant of the oil. What is the dielectric constant of the oil? 2. Has a capacitance C. If the oil is now removed, then the capacitance of the capacitor becomes, means what? Initially we have oil that is kept in the region between the two capacitor plates. Capacitance they are saying is C. Means what is the C value? If you take the area of cross section of the plate is A and the distance between the two plates is D. They have not given us these values, but we are taking it so that we can write the expression for the capacitance. What is the capacitance? There is a dielectric medium K. What is the capacitance? K times A into epsilon naught by D. This is our first case. Now second case, we have simply removed. Everything else is going to remain as it is. We have removed the oil and now the medium is what? Simply air only. So what is the capacitance here? It will be what? A into epsilon naught by D. Which is what? Look at this. From the equation 1, what is A into epsilon naught by D? We have to take the K to the other side. What is it? C by K will be. So what is this A into epsilon naught by D? This is C by K. So the modified capacitance is now what? C by K. But what is the K value? They have given us the K value. K is what? 2. So the modified capacitance is what? C divided by 2. What is the correct answer for this? Option D is the right answer. Next we have a question that has come in the year 1998. A hollow insulated conduction sphere is given a positive charge 10 microcoulomb. This is what? Hollow. Hollow means it is like a spherical shell. What will be the electric field at the center of the sphere if its radius is 2 meters? Now think about it. If we have the shell, this is not a solid sphere. This is what? A hollow sphere. Means it is a shell. Charge will be only on that surface. Charge will be only on the surface. As a result, right, the electric field inside the shell will be 0. Now this is something which is often seen as a important electric field distribution. Charge on an spherical shell, the electric field created by it inside will be what? 0. Outside will be KQ by R square, where R is the distance of the point from the center of the shell. So here anyway, they are asking us what? Electric field at the center of the sphere. Means at the center. Everywhere inside is what? 0. It need not be just the center. Everywhere inside will be what? 0. So what is the correct answer for this? So here the radius value doesn't even come into picture. Answer is what? Option C. So here these wordings, right, are little bit confusing. When they say hollow, means it is a spherical shell. That itself is sufficient. We don't need to bother about this conduction sphere. Even if it is a solid sphere, made up of conducting material, even if it is a solid sphere made up of conducting material, right? Then in that case also, the charge or any conductor will be residing only on the outer surface. So whatever the result we have in the case of spherical shell, right, same result we'll have in the case of the solid conducting sphere also. When we say a solid means what? There is a bulk or matter in the volume of the sphere. That is what you call as a solid sphere. Hollow sphere means like a shell. A particle of mass m and charge q is placed at rest in a uniform electric field E. Means what? Let us say there is an electric field E like this. We are keeping a charge q of mass m which is initially at rest. Means the initial velocity is going to be what? 0. Now since there is an electric field, right, this will start experiencing a force. Force experience will be equal to what? Q times E. And that will generate acceleration. Acceleration will be what? Force by mass. What they're asking, the kinetic energy attained by the particle after moving a distance y. Means if this charge is moving through a distance y, means we can also take it as what? Displacement, because it is motion along a straight line. For a displacement which is equal to y, they're asking what is the kinetic energy attained by the particle. So what is the kinetic energy value? Half m into v square. V is the final velocity. So look at it, what do we have? We have acceleration, we have displacement, we have initial velocity. What is the final velocity? Final velocity is what? V square is equal to u square plus 2as. That is the formula, right? U is anyway 0. So 2 into a is what? QE by m into displacement is y. This is v square. So from here v will be equal to what? Root, we don't need to get the v value also, because anyway in the kinetic energy formula will require v square. So look at it, as it is, substitute the v square. Half into m into, in place of v square what will substitute? 2 QE by m into y. So here m is cancelled, 2 is cancelled. What is it? QEY. This is what is the kinetic energy. So using the kinematics equation, right, we are able to get what is the square of the final velocity. And that is what is needed for our kinetic energy calculation, right? Half mv square formula. So correct answer for this is option A. So this is about this part video, and we'll see in the next part.